Okay. So welcome back after lunch. So my name is Duccio Fanelli. I'm a professor of physics at the University of Florence. And today I'm chairing this session, which is devoted to discussing causality from a physics point of view, and I guess with some historical touch. So it's really a pleasure and a privilege for me to introduce the speaker, Professor Alessandro De Angelis. Alessandro is a professor of experimental physics at the University of Padua and also professor of astrophysics in Lisboa, Portugal. Right now he's on leave as a scientific counselor at the International Organization in Paris, and he had a long career as a physicist with diverse interests over the years. So he began as a theoretical physicist. Then he moved to high energy physics, so particle physics, and he had a long position as a staff member at CERN. And then more recently, from 2000 or so, then he got interested in proposal, construction, and data analysis of new telescopes, especially for gamma ray astrophysics. So he's very well known for this part of his work, to which he devoted a lot of energies and time. And also, and I think this is relevant for this community, he has been studying history of physics and science in general, with collaborations also with the Museo Galileo, where this event is hosted. And he wrote several books about Galileo, so he's really well known for his knowledge in this field. So I really look forward to listen to your lecture on this beautiful topic. Thanks a lot.
Thank you. So thanks a lot. I start apologizing because I will use a bit of a different language and I will not give answers. When I was asked to do this talk, I was very happy because I thought, okay, so finally I can study a definition of causality in physics. And then in the end, you will see that I didn't succeed quite, but I learned a lot. I mean, next time, when I speak about causality in my lectures to the student, I will understand that I'm walking on a rope. Now I know it. And so normally what people expect from a physicist, people expect a baseline definition. Like, for example, what is love? And then you say, no, love doesn't belong to physics, but we can compute the probability that in a system, in a gas of monatomic atoms, that two atoms get closer than a distance lambda in the next second. And this is related to love, to falling in love. Somehow, I mean, it's a basic model of falling in love. And then people implement the model. So this is normally the baseline that we give, but in this case, I don't know if I will be able to give something like this. Okay. So causality seems a genuine physical problem. I learned from the very interesting, there was a very interesting discussion about causality relationship between human activity and global warming, for example. And this is in my job, in the job that I'm doing now at OECD, we discuss a lot. I mean, things like this we discuss a lot. And people normally say, okay, there is a clear causal correlation. So let's see if we can say something like this, at least set the stage for a definition which has a mathematical background, because in the end, physicists use mathematics, the basis is mathematics. So if there is a minimum set of assumptions that we can do in order to give a definition, which is a baseline, a minimal definition. So then the problem is, okay, the problem of finding real correlation, estimating the probability of a correlation, this is a problem for the statisticians like you. But for us, the problem could be to distinguish causality from correlation. Is it possible to distinguish causality from correlation? So I will start with the first attempts to define causality, which in a formal way are due to Galileo. So we are in the right place, and this is probably the reason why they asked me to give this talk. And then I will make an excursus to modern classical physics. I will not touch quantum mechanics. I'll just give one slide on quantum mechanics, because there probably most of the work is to be done, but also in classical physics a lot of work is to be done. So I anticipate my conclusion, but do you hear in the end or in the end of the room? Yes? Yes? Okay, fine. So I anticipate my conclusion, and my conclusion is that despite the fact that this is a very basic problem, louder. Well, louder. I don't know if I can speak louder. Is it? This is the maximum. I normally speak loud. Okay. So I try to speak closer to the microphone. And we will see that despite the fact that this is a very basic problem, that we should be able to solve it, a formal definition of causality in physics is extremely difficult, if not impossible. And this is not my opinion, but it is the opinion of Bertrand Russell, for example. Okay, as you know probably, the first formal treaty on mechanics is Discorsi e dimostrazioni matematiche intorno alle nuove scienze from Galileo Galilei. And this book was printed in 500 copies in 1638. It is the last... somebody, yes. No, it is the last book. No, I thought that it was a resonance on my microphone. So it is the last book by Galileo Galilei. Galilei will die in 4 years after publishing this book. I believe that, certainly one of the original copies, but I believe that the copy annotated by Galileo is on the 3rd floor of this building. So you can ask, but I believe it is there. If not, it is in Santa Croce. It's not in the National Library of Santa Croce. So it is here in Florence. And in this book that I like a lot, Galileo formalizes the two new sciences. We will see these two new sciences. Okay, they are statics and kinematics. And he formulates the principle of inertia, which is very important. So he establishes what is the state of unperturbed motion. He says that the state of unperturbed motion is rectilinear motion. Before, people believed that the state, the neutral state, in the absence of interaction with the external world, was rest. And Galileo redefines this and says, okay, it is rest or uniform motion, which are two equivalent states, which is very nice. And this, by the way, we call today the first principle of mechanics, or principle of inertia. Galileo had started writing this book already in Padova when he was young, and then he stopped because he went to astronomy, because he discovered that it was very interesting to observe astrophysical objects with the telescope. And then he was absorbed by astronomy for a lot of time. Then he went to cosmology. He published the Discorso sopra i due massimi sistemi del mondo in 1632. And then finally he took back his notes, these lecture notes in Padova about mechanics, and he started writing them down in a book, which is a masterpiece. According to Hawking, it is the best book by Galileo. And the style is 4 days of dialogue. Normally, Galileo is 3 friends talking. Salvati, Sagredo, and Simplicio. And Salviati is a gentleman from Florence. Sagredo is a gentleman from Venezia. They were both died when we started using them in the books. So he wanted to celebrate his friendship with them. And then Simplicio, that is a professor, not very smart, a professor, an Aristotelic professor who plays the role of the guy who defends the institutions and the common thoughts. Okay, and there is a lot of discussion about the origin of the name Simplicio, which somebody attributes to a commentator of Aristoteles who lived in the 4th century after Christ, and somebody attribute to a joke like Galileo was doing often, simpliciter, like simple-minded. Probably, knowing Galileo, I mean, it was a mixture of the two things. Okay, the dialogues are witty, the guys are really, really, really witty. And this style of the dialogue is very good because Galileo then can do several things. First of all, many times the demonstrations by Galileo are not formal. They are not. In fact, sometimes he's wrong, but sometimes he's right. But so he wants to say more than he can prove mathematically. And the dialogue is functional to this because sometimes he says, look, I think this and this, but why, and so on. And under this dialogue, he convinces you that something is true, even if it's not formally true. And many times, he's right. Sometimes, he's wrong. But still, he can cheat you very, very easily. There is another physicist, famous Nobel Prize, Richard Feynman. Probably you saw the book 7 Short Lectures of Physics. Okay, Feynman wrote one of the best books of physics, the Feynman Lectures of Physics. And then, for example, for some time, I was using a demonstration by him to teach my students the Maxwell equations, some equations, and you'll see them later. And then I understood that he was cheating a bit. So, just oversimplifying, okay. So, in this dialogue, the fiction of the discussion among the three characters is even smarter than usual because the three friends meet and they comment a book that one of them found by a professor in Padua. So Galileo could recycle his lectures in Padua for the book. And the book that they comment is written in Latin, and it contains only formal demonstrations. So whatever is written in Latin is correct. The friends comment and they say then some make some corollaries and things like this, which are sometimes wrong. And they are written in vulgar, in Italian. So what is in Latin is foolproof, what is in Italian is 90% correct. The two new sciences are, in the first 2 days, the science of materials, which is done with a very good approximation. So he makes a lot of theorems, fantastic theorems about the stability of the structures, the relationship between size and resistance of materials and so on, the resistance of bars to pressure and things like this, to weight. And the last 2 days are mechanics, which is basically kinematics, so the science of motion. What is incredible is that the style of the exposition is the same style that we use today in the university. So we have these formal courses in the first 2 years of mathematics, physics, engineering, and so on. And if you look to our style of teaching, it's the same style that Galileo used in this book, which is good and bad. I mean, good for Galileo, probably not very good for us if after 400 years we continue to teach in the same way. But okay. We learned this. As you know, I mean, we are professors, so the important thing when you teach is that you feel safe. This is the most important thing. Okay, by the way, you can download for free, if you have the link to the Springer site, or for free from the infamous Russian site LibGen, this book in which I translated the book by Galilei in mathematics, because Galilei was not using mathematics, he was using Euclidean geometry. So it is not very easy to read. And so I made an effort. Thanks to the COVID, I could translate the book into, yes. Okay. So I don't know what is the most important thing in this book. There are several opinions. For Giovanni Di Pasquale, I don't know if Giovanni is here. Yes, it is the plane, the piano inclinato, the inclined plane. But there are a lot of other things. I mean, for example, for Galileo Galilei, the clear opinion. For him, the most important thing was a theorem that he said for many times in his essay, saying, I will be remembered for this theorem, for example. He is not remembered for the theorem, but the theorem is very elegant. And in the last point, there is a corollary which is wrong, badly wrong, but okay. Anyway, so to me, the main aspect is the definition of an unperturbed system, so the principle of inertia, because this is a basic principle. Okay, so Now Galileo thinks about the causes. So he described the motion of the rectilinear motion, and then he describes the uniformly accelerated motion. So the motion under the action of weight. This is very elegant with the inclined plane, and then he extrapolates to projectiles, he makes some exercises in what's the name? Artillery. He makes some exercises in artillery. And then he faces the problem of the cause of the motion. So motion in late sense, what can change inertia? Now, I say this for the Italians. Now, the change of inertia since in the last years has become a very common expression also in the football matches. If you hear the comment to the football matches, they say the inertia is changing. And you say, what are they talking about? So somehow they took from Galileo this expression, which now, nobody, 20 years ago, nobody could think possibly of the change of inertia. But now, thanks to Sky and the other TV channels talking about football, when the equilibrium in a match changes, it is a change of inertia. Okay. So what is changing the inertia is the problem of Galileo. Of course, in Newton, we know the solution. F equal to ma. A is the change of inertia. F is the external actor which changes inertia. Okay, Galileo had promised the publisher, which is Elsevier. By the way, you noticed the symbol of the editor, right, of the publisher in the first page. It is Elsevier, okay, which now has a reputation not as large as it had 400 years ago, but okay. Elsevier, by the way, we write a preface to the book of Galileo, and it is a great preface, full of curtain. So Galileo promises the publisher a final day of discussion about the causes of the motion, so the dynamics. But he's not satisfied with this result. So he says, I will not be able to publish the last chapter. The editor, the editors are there, they are. They say, give me the book, give me the book, give me the book. So in the end, he gave the book, but he replaced the fifth day about dynamics, the causes of the motion, with a boring, very boring, mathematical appendix on the calculation of the center of gravity. Are there many mathematicians here? Okay, this calculation, integral of x times blah, 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 the rho of x, blah, 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 blah. Okay. So this is the last chapter in which he tries, without mathematical analysis, to perform a general calculation of the center of gravity. But he will continue to work to the fifth day until his death. I recently met a guy who was writing a tragedy about the work of Galileo on the dynamics, trying to understand what we call the second law of mechanics or Newton law. Okay, so there will be a tragedy on this, and in the end, it will be published posthumous by his disciple Vincenzo Viviani, which is buried, by the way, 100 meters from here, together with Galileo. So, he didn't kill him. It's not like the pharaohs with the cats. They say, you are my best students, I kill you. No, it's not like this. Okay. Because he survived and he published the fifth day. And the fifth day is, he worked a bit on the fifth day. And now the fifth day is called La Forza della Percossa, the force of percussion. So, in the fifth day is a bit atypical because there is no more Simplicio. Simplicio is replaced by another disciple of Galilei. Now the three characters, there is no more a character which disagrees with the others, but the three cooperate towards a common truth. And Galileo presents two kinds of mechanical forces able to change inertia, which are weight and percussion. Percussion because you understand that, for example, with the same weight, if you hit with a hammer, you obtain an effect that is difficult from just posing a hammer on top of an object. So he tries to formalize this, but it doesn't succeed. The fifth day is very nice, but is not very conclusive from the point of view of physics. So basically, Galileo fails in finding the cause of the inertia. So the first attempt to introduce a concept of cause in physics is a failure. By the way, he tries to formalize the concept of momentum, so mass time velocity. You can understand the effect of a percussion, depends on the mass and the velocity, but it doesn't succeed because he mixes energy and momentum and so on. So it is not very clear. Okay. By the way, the first formalization of the causes of the change of inertia is in the Principia by Newton. Newton is a fan of Galilei. He will use in many, many occasions the works of Galilei. And for example, also in the gravity, in this book, I mean, when Newton computes the gravity, he uses example from the motion of the satellites of Jupiter computed by Galilei and so on. So it's not just that he looked to the moon, like they tell us in the high school. It is more complicated. And it is clear that Newton knew very well the works of Galileo. So the second law is F equal to ma, and this is directly related to the principle of inertia and the change of inertia. As a matter of fact, Newton is very generous, and he tells that both laws of dynamics are due to Galileo. We don't believe this today. We think that this was very too generous. So he says, and you see here the first two laws as Newton enunciated them, and it is the same way in which we tell them today after 400 years. So the first law is Galilei's law, the principle of inertia. All bodies persist in a state of rest or uniform rectilinear motion until forces applied to them make them to change the state. And the second law is the change of motion. This we call Newton law today. Is the change of motion is proportional to the motive force impressed, and is made in the direction of the straight line in which the force is impressed. But then Newton says that it was Galileo who, thanks to these two laws, understood the law of motion of gravitational motion, and to the law describing the motion of projectiles, the parabolic motion of projectiles, confirming this with experience. Okay. In the conditions that there was no air resistance. So really, I mean, these people were thinking really a lot. I mean, it was every word here has a weight. Okay, so this is the explanation of causes according to Newton. Now, let's analyze a bit mathematically the causality in the Principia of Newton. So, force is the cause of the change of inertia. So first there is, for example, inertia, then there is a force, then a change of the state of inertia. When I say first and then, I have no problem, according to Newton, to define this, because there is if you read the Principia, there are some theorems, and then in between there are some scholiums, some intermezzi, some parts in which he discusses some things, like some hypotheses. Okay, he says, I don't make hypotheses, some assumptions, some evidences, and things like this. And he has a scholium about space and time, in which he says that the time flows independent of the physical universe, which is very interesting. So it doesn't have problems in time. What is first and what is next is depending on an absolute flow, which simplifies a lot causality. Okay, then somehow he makes to understand, Newton makes to understand that action can happen at distance. So for example, in the gravitational force, a body influences another body instantly. This is still a matter of discussion. So if I gravitate around another body, it is still a matter of discussion what is the time of propagation of the signal in a constant motion. It's not obvious that the speed of propagation is the speed of light. So this is an open question still in physics. Okay, and all this is coherent within a simple model which is somehow unsatisfactory in the sense that it assumes that time is transcendental, and the third law of action and reaction is difficult to encompass on this. So when I make an action on you, you make an action equal and contrary to me, but when? I mean, at what time these actions are equal and contrary? What is the cause and what is the consequence? Am I making an action and you react, or what does it mean, this in physics? So as you can see here, causality is imposed in the model, but not in a completely satisfactory way. Okay, in the 18th century, a new formulation of physical laws enters in the field, and it is a game changer because it is a conceptually simpler definition of the behavior of the system. It is a definition in which you can, for example, if you want to solve by force, by the mechanism of forces, a system in which you have a pendulum, then another pendulum, this is very, very difficult to do with laws of Newton. But there is a formulation in which you just write a function L, called Lagrangian, which is a function of positions, let's say coordinates which describe the position of objects, and generalized velocities characterizing the motion of the system, and of time. So you write this function, and then you have some operations which describe you the motion. And the point is that, okay, and then 100 years later, sorry, I wrote José Louis Lagrange 1970, but it is 1790. I'm dyslexic a bit. Okay. Okay, and then 40 years later, Hamilton made an equivalent formulation through a conceptually similar function, which is called the Hamiltonian. Okay, still a function of the same kind of positions, velocities, and so on. Okay, so given a system, you can derive the laws of motion once you describe this function and the roles of potential energy linked to forces and kinetic energy are separated somehow. But you know that they are separated, but they don't have a special role. So you cannot say that kinetic energy is the consequence and force energy, potential energy, is the cause. Somehow they are embedded in all this. You can then interpret the solution as one being the cause and the other being the consequence. So, like the philosophers, some philosophers like to say that the laws of motion don't appear but can emerge. And the concept of emergence is very critical and subject to different definitions. What is emergence? So you have an expression and you say, look here, there is not F equal to ma, but it emerges. What does it mean? It means that the equation contains more than it terms. It cannot be. It means that you didn't expect it and it emerges maybe. It's more likely. It's a better definition of emergence. Okay, it was unexpected. Somehow, if you look to the Lagrangian, if you are not an expert of Lagrangians, you say, but what is the cause and what is the consequence? Okay. If you saw many Lagrangians, you can say this. So the point is that this formulation is so convenient from the mathematical point of view that basically nobody nowadays splits anymore the motion between cause and consequence. We just write a Lagrangian and then we let the mathematics do the job. Now, a very nice analysis, both philosophical and mathematical, which is to me the same, I mean, this is was done by Mach and especially by Bertrand Russell, who wrote a paper that I like a lot in 1912, which is called On the Notion of Cause, in which he tries to formalize at least a minimum set of assumptions that should be the basis of a definition of causality in physics. So what more or less I wanted to try to do here, but I thought, okay, if Bertrand Russell didn't succeed, we'll see that he didn't succeed. I have no hope of doing it. But let's say, what could be a minimum, a baseline of the cause of the definition of causality? So, for example, to go back to the example of today, does the statement the cause of global heating is anthropic? Does this belong to the speakable in the realm of causality? This is the question. Okay, I will go back to this question because this is a cause of a lot of polemics nowadays in my university in Padova. And so, okay, does this belong to the speakable? Okay, so the discussion by Mack and then the formalization by Russell, the better formalization by Russell, goes along four main lines. One is that the notion of cause and effect are intrinsically vague. And this is especially true for situations in which there is a feedback loop and you cannot really separate one thing from the other. Like it was, for example, the ozone hole. This was a case in which, reconducing it to simple physics was not easy, and in fact, the people who tried to do it were wrong. Then, a distinction between causes and background conditions cannot be drawn in physics. This is, in statistics, the problem of noise in the data, and this problem doesn't have a philosophical intrinsic solution which can be mathematically stable and solid. In particular for physics, the causal relationship should be relationship between events which are spatially localized. So if I say that I kick a ball here and the ball goes there, the ball should be in a very precise position, then move. My foot should be in a very precise position, then move. And all the rest happening in the universe should be irrelevant down to a certain interval of space that we will see what can be. For the moment, let's say a reasonable interval of space. Max says a reasonably isolated system. And this is the so-called locality challenge. So somehow physics should be local. Since we cannot know all the universe, it should be assumed that only the parts of the universe that we know influence the motion of the objects that we study. Okay, and finally, the notion of cause is generally taken to be temporally asymmetric. So first there is the cause, then there is the effect. And this is difficult to accommodate in a physics that, like classical physics, for a few body systems, is intrinsically symmetric in time. So it has second derivatives, so dt squared minus t plus t goes away. Okay, and this is the time asymmetry challenge. So this is the first intrinsic problems that Mack and Russell evidence. This is water. Can I use this water? Yes. Okay. Russell tries in his article that I invite you to download several definitions. This is my favorite. He finds in the end that all are unsatisfactory. This is my favorite for the moment. We will see that I will discuss a bit why he thinks that it is not completely satisfactory. I also think this. And that this definition is that given an event E1, there is an event E2 and a time interval tau such that whenever E1 occurs, E2 follows after an interval tau. E1 can impose also the necessity of E1 to E2 or not. If you impose it, then you restrict a lot the sample for which you can speak of cause and effect. If you don't impose it, then, okay, for example, you can say that the day is caused by the night, for example. I don't know if we want to say this. It's a matter of definition, but do we want to say that the cause of the day is the night? Okay. What is an event? Well, an event, it is something changing or a point in space-time. Also there we should define what we want to understand by an event. Relevant for the discussion of this morning, how long may be the time interval to cause, between the cause and the effect in order to interpret the two in a cause-effect relationship? Well, today we learned, we knew already, but in the global warming, you have something that started before we can say it is a cause. And that will continue after we start determining the effect. So in this case, the time interval tau spans through the cause and the effect. So it is difficult to frame a problem like this in this definition, which is anyway a definition that Russell finds even too generic. So I have the impression that it is difficult to frame this kind of problems in a real causal relation. Now I go to the example, to the said example. I sit down a bit, so I'm not used to teach anymore. Now we go to the example made by that I was making before. Recently, some very known professor of my university published an article saying that the statement that global warming is anthropic is not a scientific statement. And they were crucified by the community of the university, saying you deny an experimental evidence. But in fact, they were just making a philosophical statement that cannot be condemned. I mean, a physical statement, I don't know how to call it. But as a matter of fact, they were really crucified also by the journal. They say, the journals, of course, were saying, the local journal was saying, Professor Barbieri, just to say a famous name, doesn't believe in global warming. But no, he was not. He said a different thing. Okay. He was speaking about causality. Okay. So the difficulties of this definition is that it is by no way a general definition, and also the number of cases that it can account for in classical physics is very limited. And ideally, it works if the action is instantaneous, time is very short, and then you have the reaction, which is the world in which was Newton was operating. But in general, life is not like this. Even in physics, life is not like this. You have courses which span an interval of time. Like even if you hit a nail with a hammer, this is not an instantaneous process. So it is difficult to frame definition of causality, even for simple events, and even with this reductive assumption. A further complication is given then by a new paradigm in physics that is proposed after in the 18th century by Faraday and Maxwell. And this paradigm is the seminal concept of field. So now you don't have anymore an interaction between A and B, but the interaction is mediated by a field, which is a change in the characteristics of space given by the presence, for example, of a particle with given properties. So this is the definition in the Britannica. As you know, Britannica had in the past the best authors about physics, like Einstein and so on. Now it is a bit less good, but still. So a field is a region in which each point has a physical quantity associated with it that can be a number or a vector. Okay? And then it gives some example. How does this comply with causality? Well, a deterministic. Now we start mixing causality with determinism. I say that a system is deterministic if, knowing that the system at a time t, you can compute the characteristics of the system at a later time. And a deterministic definition of causality in the fields is that if you know the fields at a time t, you know it at later times. Okay, this can work coherently if you have in the same equation the field and the particles. Okay, I put just there for graphics. I mean, I believe that some equations are beautiful. I don't want to discuss the meaning of them, but I put them because they are not so beautiful, but then they will become beautiful a few years later, the Maxwell equation. So somebody finds them beautiful. I don't find them beautiful before something will happen 50 years later, then they become very beautiful. But for the moment, you see that you have two fields, E and B, and then you have two causes, which are the density of charge, ρ, and the current, J. Why we say, I mean, this is just an anthropic point of view. I mean, we say that the current and the charge are the causes and the field are the consequences. But the mathematics of the equation doesn't say anything like this. So causality has completely disappeared from these equations. I don't know if you agree or... So you don't see causality here. Okay, these equations are suspect of action at distance. So there is also there a lot of discussion still ongoing. And then you have a law, I mean, describing the real change in inertia, which is called the Lorentz force law, which again depends on the charge and on the density of current. Okay, the next game changer is special relativity, in which there is a further complication. So time is no more allowed to be absolute. So delta t, the interval of time, can change from a frame of reference to the other. If I walk, there can be a change in the mutual times of events. And then we should be sure, we should have some mechanism to protect the fact that if we want to say that an event is caused by another, it cannot happen that the thing reverses in another system. So we want to say that causality must be preserved by the change of frame of reference. This is again an assumption, this is a postulate. Okay, you saw the movie Back to the Future. So suppose that the guy, I don't remember the name of the guy. I'm a nerd, but I forgot the names of the guys. So you know the nerds like a lot Back to the Future. It is a... Okay. So if the guy was ready to fall in love with his mother. So what could have happened in this case? In the past. Okay, so there should be a protection mechanism against this. And this is represented by a plot that is a visual plot, that is this plot, in which given a time, which is the red point, this is, for example, now, all the future is in a certain region of coordinates in space and time, and all the past is in a certain region of the possible space and time coordinates. And this, I don't know where is the facility, okay. And this definition preserved the basic definition of causality, provided the interactions between 2 points travel at a speed smaller or equal to the speed of light. So the fact that the speed of interaction is equal or smaller to the speed of light is not a law of physics. It could be that the speed of propagation is larger, but it is the only way not to kill completely the idea of causality. So it is an assumption that we make. Tomorrow, it could be that this changes and then nobody will be allowed anymore to speak about causality. As you can see in this system, okay, this is a projection of the cone that I showed you before. If the speed of signal is always smaller or equal than the speed of light, then A can cause B, in a simple definition like the one that we gave, which applies to the very limited amount of phenomena. but there cannot be a causal relation between A and C, because this could be reversed by a change of system. So if we don't accept that the communication happens at speed smaller or equal than the speed of light, then we have to give away completely at basic level any relationship of cause and effect. Could be, but we hope no. Okay, this is due to the special role of the speed of light in the theory of relativity. Okay, by the way, a corollary of this that I like a lot, if the future and the past are well defined by the causality relation, as you can see, if you have an observer, now we are here, suppose, now we are here, and then we pass 10 seconds and we are here. As you can see, our future in 10 seconds from now is smaller than our future 10 seconds ago. So there is a formal demonstration of the fact that as you get older, the space of the things that you can do shrinks. This is a demonstration, corollary that I got. My best theorem, I would say. As you get older, you can do less things. Nobody demonstrated it formally. Okay. In general relativity, we still don't know if time travels are really forbidden, by the way. But at a certain level, at a level, macroscopic level, because general relativity is defined only at differential level formally. But we believe that there should be a superprotection mechanism forbidding macroscopic phenomenal violation of causality. So we don't know. I continue to use causality, the word causality, even if I didn't define causality, but I know what is violation of causality. This I can define, but I'm still not able to define causality. I'm close to the end now, because I want to give a summary of the classical view of causality updated to the present time. So we started from Galileo, then we got the first formalization by Newton, and then an evolution with Hamilton and Lagrange, and then the concept of cause and consequence and correlation is fading out. So I mean, presently most of things are correlated and not caused one by another. We cannot really isolate this. So the summary in the classical view is that now the present formulation of physics doesn't use causality as a general concept. Still, we formulate the laws of physics to prevent causality violation in basic situations. Classical physics is local, so the events, the space-time region that can influence a point is in a region near the point that we study, and it is deterministic, so we can predict the evolution. Even we can in principle predict the evolution, because sometimes, like in the three-body problem, the knowledge, this would require a perfect knowledge of the dynamical variables of the system. Okay? But in principle, for the perfect measure of things. Okay, as I said, I don't want to go to quantum mechanics, but just I put one slide because there the problem is even more crucial. So in quantum mechanics, all this frame change. So the fundamental entity of nature is a non-observable quantity, which is a wave function. This evolves through an equation which is deterministic. So if I know the wave function, I can predict. I cannot know the wave function, but if I would know the wave function, I would predict its evolution. But then, when I measure a quantity, then there is a process which is unpredictable, which is the measurement by an observer. And the epistemology of all this is still work in progress. And I mean, many physicists, you know, many different interpretations, many bottles of wine. I learned that wine is dangerous even in small quantities, but I mean, this causes enormous quantities of wine to be drunk in order to converge to an epistemology of this process. Okay, my conclusion is that, very sad, okay, before preparing this talk, I knew much more about correlation than I know now, because despite the fundamentality of the subject, there is no formal mathematical consistent definition of causality covering all and only the aspect of it. This I can say as a firm statement. In any case, causality is not a fundamental ingredient in physics since the 18th century, but we protect physics against violations of causality. And we have some fundamental aspects of causality related to simple cases, and these belong to the speakable, and all the rest belongs to the unspeakable in physics. So, thank you.
Thanks a lot, Alessandro. Questions?
Thanks. This is just a curiosity. So thanks for the talk. It's really enlightening. I'm just curious. So you said that Newton found that force is the cause of change in inertia. But what kind of tools did they use back at the time to actually say that force was the cause of a change in inertia? Did they run any experiments? How did they come up with that?
No, force is the cause that changes the inertia. If you suppose that force is instantaneous, localized, so then it is the cause of the change of inertia.
There are many things that are instantaneous. Well, how they come up with force?
Well, how Newton...
Force and the amount of force.
Yes, this is a quantity.
I don't know, eating a piece of bread, for example. That would be our weather or something like that.
Well, no, I'm also curious, but the debate about the change in the motion started formally with mathematical means, at least in the 12th century. So we have already the mathematicians in Paris, we were writing some paper about this. And it took 400 years because before this formalization. So I don't know how Newton came out with this idea. With Newton, we admire Newton a lot. And still, this concept F equal to ma is the concept that allows us to send the satellites in space, for example, to move to the moon. So it is a great concept. But beyond a certain level, it doesn't work anymore.
I was just asking because it was related to Lee's comment before how we can summarize evidence, come up with a slide. And this is a nice place to do the summary.
Yes. But we have to simplify reality.
Yeah.
Yes. Reality can be simplified, but not beyond a certain level. It is another one.
Well, first, thank you for telling us that when we get old, there's less things we can do. So I have a formal justification to my boss that I'm not going to do much. Thank you for that. But serious question is that you talk about this impossibility to define the causality, but is there a notion of the causality more quantitative, like the degree of causality, the resolution of the causality? What I'm thinking about taking the climate change, right? You have global change, you have local change. How the global change is defined as aggregation of the local changes. So is there a formal notion to think about the degree of causality, then somehow the grandest causality is the limit of all these things accumulated? Is that such a study?
No, the point is that I like this question because as I get older, my capabilities on mathematics deteriorate very quickly. I don't know for the others, maybe the others. But, I tend to do things in a more qualitative way. And I would say that, yes, we can formulate definitions of causality which are less strict. But when I was 25, for example, I would never have accepted this kind of definition. So they don't belong to the purity of physics like a 20, 25 years old ideal mathematicians or physicists conceive as acceptable. And these 20 to 25 years nerds are the people who change the world in the end. So we should respect them. So as you get old, you can get more general definition, but they don't belong to the world, to the purity or the beauty of the mathematics.
Yes.
Hi. Thank you for your talk. I have a question. Can you please clarify with an example, maybe the instances when physicists need to protect causality, but how can they do it if they don't define it? So can you give an example?
Yes, I give you an example. Suppose that in a frame of reference, let's say, seen from the Earth, my mom, I don't want to use my mom, the mom of my cat. I don't have a cat, so I don't risk. No cat were killed in this example. The mom of my cat dies after generating my cat. And suppose that now I compute the equation of motion of this system seen from a galaxy far away. And this galaxy far away, the mom of the cat dies 9 months before generating the cat. So this should be forbidden by physics. So I don't know that this kind of violation of causality should be forbidden by physics. Yes, yes. The most striking example is the inversion of temporal sequences. There is no natural law of protection.
Currently in physics, you are considering the Russell's principles, for example, like they are, agree upon certain principles.
Yes.
And but they are, but they are like unwritten, like.
They are, well, they are axioms, yes. They are, I don't use the word unwritten. It's not a secret to say, look, don't violate. No. Don't allow the mom of my cat to die too early. But we basically impose this. The fact that the speed of signals cannot be faster than c is due to some mathematical problems that could be overcome, and to some intrinsic problems that we don't want to overcome. But of course, the point, as I was saying, physics is an experimental science, so maybe tomorrow somebody will find a signal faster than C, and then we'll think about it. Thank you.
So while I move there, perhaps I can mention the thermodynamics. So the fact that entropy grows
yes.
sets the direction for the time arrow. So this helps
yes.
us to believe in what we're doing when doing physics. Otherwise,
yes, in a complex system, you have a preferred direction of time, which can be, according to some heretics, also a definition of the arrow of time. Which can be also, a loop, like Prigozhin. I don't know if Prigozhin is heretic. Is heretic? Do you think that Ilya Prigozhin is heretic, or?
I think you made interesting
yes.
contributions, but okay.
He's interesting, yes. He's a bit crazy, but yeah, okay.
So, thanks a lot for your talk. I'm not sure I followed 100%. And so what I'm saying is probably also very simple-minded. But first, a question and a comment. You are saying in your second bullet there that causality is not an ingredient of the formulation of physical laws. Yes. I've always thought and interpreted physical laws as causal structural models of the world. So intrinsically, a physical law is a causal law. It tells you what happens to the world if we act on some elements of the law, right? What you have on the essentially right-hand side, if you move something there, something happens on the left-hand side. Mm-hmm. And so this is essentially also an alternative way of, for example, formulating in the social sciences causal effects. Mm-hmm. You can do that by postulating the existence of a structural model that tells you how the world works, or you can do that by formulating a causal effect as a contrast of potential outcomes. But even in order to postulate and so introduce these premises, potential outcomes, you need to essentially expressively define what an event is. So what a treatment is, what a manipulable variable is that index these potential outcomes. That you can possibly, they both exist, or both, or even more than two exist. Only one can possibly be, observed. The same is in physics. Once you have applied something to a cell or to something, you are, you cannot turn back in time and do an alternative action, but you still have a law. So you are still thinking of that you could have done something different, and you could have observed, according to the law, something different that follows the law. So my question is, why are you saying that causality is not an ingredient of the formulation of physical law? Because to me, this is essentially a way of formulating causality.
Well, so technically, what you do is that not to introduce some causes and some effects. You introduce a description of the environment, and then physics predicts the evolution of the environment. To isolate a single factor as a cause of the evolution of the environment, it's a different story, and this is not easy. Second, when you say that
you are saying that the physical law is not replicating over time?
Yes.
It's stable, right?
Yes, it is replicating all the time.
It's not only about predicting in the future, it's something that you always applies. So it's kind of having a deterministic, I don't know.
Well, but one thing is determinism, and one thing is causality. So determinism is that I describe a system, I predict the evolution.
An extreme version of causality. No, I don't know.
Or a reduced version of causality, I don't know. But then the second thing that you say is true. I mean, I introduce some variations and I see the effect of the variation. This still you can do. So I write a function, I predict the evolution of a function. This I can do. I don't know what is the particular actor which is changing the thing. This I don't know. So I don't know the cause. And I know what happens if I inject a variation. Yes, this I can do. So in part, physics is not useless. Physics is useful, but it doesn't answer you completely on the cause and relation effect. This is what Russell says, and I agree.
It doesn't, as what we all do, is not that we are describing the whole world and how world, every single event that happens in our life. We're not trying to explain all the deterministic or non-deterministic causes of that, of what we observe. Still, you can, for example, run experiments to see if your physical laws are valid.
True.
And what you do there, you essentially replicate and change some of the features in the law. True. And see what happens.
True.
And this is an exercise that either with experimental or observational data, we are trying to also do. So, again, maybe simple-minded, maybe, but from someone that was good at math but has never been good at physics, I do not fully agree with your second bullet.
Mm-hmm.
But this is probably for...
No, but I mean, what we are defining is determinism, and the classical physics is deterministic.
All right, thank you.
With some nuances related to the knowledge of the initial condition. Yes.
But maybe a way to rephrase the question is, why, from your lecture, I gather that in physics the approach of potential outcome, counterfactual outcomes to define causality is not accepted or is not used. So we in this crowd, we define causality comparing counterfactual outcomes.
Okay.
What if? No? And,
What I mean
is this a frame of, and you said that we have no definition of causality. We have one, or at least this crowd has one.
What is the definition?
I define the existence of two potential outcomes. If I see...
That's how you measure,
No. It's definition. In fact, I observe only one.
They don't have everything in their framework. They miss the treatment. They leave everything.
Well, the treatment is the kick to the ball. So
Yes.
there are two potential outcomes. There are two potential outcomes. The ball moves. The ball doesn't move.
No, I'm not saying that there is no physical phenomenon in which you can talk of causality. But I'm saying that there is a limited amount of physical phenomena for which you can give a definition of causality. In general...
No, but but shouldn't we distinguish the definition of causality from the possibility of assess whether there was a causal effect? We can still define it and maybe not be able to establish whether there was a causal link or not. These are two different things, but I still can use the potential outcome framework to define causality.
Okay, you measure, yes, you measure if you can, then you have three possible outcomes. There is causality, there is no causality, I cannot say anything.
Exactly.
In many phenomena, in physics, you cannot say anything. The set of phenomena in which you can say something is very limited. What is the point?
Just another curiosity, if I may. You never mentioned David Hume. Is it because he's a philosopher?
No. I actually wanted to mention David Hume, but I skipped him. Yes, I skipped him, yes. No, I thought of mentioning David Hume. I mean, yesterday I thought maybe I should add something about Hume, but yes, I didn't add anything. I constructed a leg to skipping Hume, but I thought of inserting Hume, of course. Yes.
Can I say something?
Sure.
My iPhone, because otherwise yeah. Maybe, okay, I have in mind the example of I have a pencil in my hand, I leave the pencil fall, and the pencil falls. Us as causal inference people, maybe we are thinking of causality as my action of leaving the pencil, but not an ingredient of formulation of physical laws is that the gravity doesn't require me leaving the pencil falling. I don't know if I'm clear in my thought.
Yes, no, but in the case of gravity, of the fall of gravity, I can believe that if you don't ask yourself too many questions, if you have a classical view, you can say that the force of gravity is causing your pen to fall on the floor, yes?
The cause is
yes.
Okay, the gravity is the cause in that case.
You can call the gravity as a cause. Then, of course, you can ask yourself, what is the cause of gravity, since it is a field, so you can say the field has some field equations. But if you just limit yourself to a knowledge which is not the extreme knowledge, in this case, I would say that you can build a valid model of cause-effect, yes.
So, in this particular case, it's the gravity.
Yes.
Or me for letting the pencil fall.
No, but then you go to a philosophical... no, then you go to a philosophical question. Okay, no, then you go to a philosophical question I'm not ready to answer. But in the question of the motion in gravitational field, classical motion in gravitational field, I can say that you are authorized to say that the gravitational field make the... Yes, this you can. It's very stable definition, yes.
So just to add a bit more confusion, I mean, all examples that you made are coming from classical physics. So you talk about balls that are falling.
Yes.
I mean, it's really, I think the concepts that you try to highlight, they span a wider range of physics realms. So I think level of coarse graining, the word to which you want to try to apply concepts of physics, experiments, interpret experiments, produce models at correct coarse graining level which have predictive power. And we should try not to confuse predictions out of a model with a foundational aspect that I think you try to highlight. I think these are all concepts which I do not control, and I discovered I don't understand things I knew I understood. But actually, we should be cautious, because all examples that you made are from a very specific physical setting, which is really too close to our everyday life. So it's really the laws of physics. They should span realms which are very, very far away from what is our intuition. So you touched in the very end quantum mechanics. So in quantum mechanics, there is the concept of entanglement. I don't know if you want to comment on entanglement. And this is, I mean, there is a very famous theorem, which I guess you know, Bell's theorem, which provides, I mean, there was Nobel Prize. Okay, but basically, I leave Alessandro the microphone so he can comment on this, but basically, a couple of years ago, I guess there was a Nobel Prize for experimental measurements on the validity of Bell inequality. Bell inequality sets a higher possible range of correlation for classical phenomena, which builds on local realism, as you mentioned before. And if you go to the microscopic world where quantum mechanics apply, you can face correlation which are higher than the limit that applies to classical phenomena where local realism occur, as you mentioned. So it is completely a different story. So you can have two particles which are very far away, one from another, but they talk, they keep on talking, and this is really an important point, which is driving also a lot of technological development using the laws of quantum mechanics. So I think scales are important.
Oh, basically, the Bell theorem. Okay, the Bell theorem. Formulating the Bell theorem is a mess in the sense that the enunciation of the Bell theorem is one page, basically. But the Bell theorem, which is one of the best theorems of the century, together with the Gödel theorem, I would say Bell theorem, basically implies that the influence on reality at basic level can be non-local. That means that the evolution of a system can be known only if you know something that is so far away that you cannot know it. So basically, it's a non-local theorem. So it is impossible to know. It's an impossibility. Yes, but it is done it is a constructive theorem. This is incredible, like the Gödel theorem. It is an impossibility theorem done with a constructed proof. And this, to me, is a masterpiece, yes. So, and okay, Bell didn't win the Nobel Prize because he died before. So the people who demonstrated it experimentally got the Nobel Prize. But, I mean, at the very, very deep level of physics, quantum physics, if quantum physics is true, which always we have to say, causality at fundamental level doesn't exist because things depend, not depend, but the evolution of a system, in order to be described, will require the knowledge of things that are too far away for you to know them. Okay, so like the Gödel theorem, it is a desperate theorem, but it is a theorem.
And also, if you
put some constraint, you can define it.
No.
If you leave it,
no. Even if you put a constraint, things there, I mean, a guy on a far galaxy, for example, measures now a neutrino. He says, "Ah, look, I found a neutrino, a tau neutrino in a detector." Huh? By the way, sorry, you will know in a few days that an Italian detector detected the energy neutrino for the first time. Okay, so a guy with a detector in Sicily measures a neutrino, and then a guy on a quasar far away, finds that there is a change of gravity, and he doesn't understand why.
Instantaneously.
Instantaneously, yes. So this
because,
is the Bell theorem.
Because these pairs are entangled together.
So, but I decided to skip quantum physics because then I really...
No, sure. No, but just to warn that actually physics is not just what we believe comes from our intuition.
There is a middle ground in physics, like thermodynamics? I believe Carlo Rovelli had like some argument where he said actually causality is built into thermodynamics. I think you mentioned entropy. So perhaps you could tell us a bit more about this, which I think is closer to intuition, but still crazy enough.
Well, but this I leave to my chairman because he is an expert of complex systems.
No, actually, it's related to what I was telling before. So at the scale of our everyday life, thermodynamic applies. And so we know that entropy should grow, and this sets a direction for the arrow of time. And so if we draw a model, which we are used to do, and we challenge the model at this scale, then today is today, tomorrow is tomorrow, and we can make prediction. And this prediction have a sort of a causality and basis. But then if you go to the microscopic scale, also the laws of thermodynamics are challenged. And you can have fluctuations. Basically, thermodynamics is just like the mean field evolution of a stochastic process. You look. No, it does. It does, but you have fluctuations, and the fluctuation can take you backward in time. But on average, you go forward. You see, that's and this is what we experience.
So on average, it works, but
exactly,
it could
exactly,
go backwards.
exactly. And there are relations, there are bounds.
So we know that physics could tell us something sure instead.
No. No, physics give answers only about irrelevant questions. Very elegant, irrelevant question. I took off the jacket. I really, this room is really heavy.
Going to first.
Possiamo girarlo verso se ti annoia.
Okay.
Okay, now I
So,
transforming myself in a real physicist.
So I start wondering if we're trying too hard, trying to define a universal definition for causality, getting to all the trouble. Because if we think about, well, let's forget a causality. Like, do we have a universal definition of association? Do we have a universal definition of dependence? Right? We use these language all the time, and we have all kinds of different versions of association dependence. We feel pretty comfortable about, right? Where stochastic, deterministic. But couldn't we work on just different versions of causality just for different purpose? With this grandiose notion, much more just like a natural language, leave something being ambiguous, just like when you talk about dependence and association.
Yes, if I understood correctly your question, because there were a lot of noises here coming from somewhere, and you ask if we can build on a reduced version of causality, which is somehow correlation or association of events. Is this your question, or I misunderstood?
No, I'm just asking whether we don't have a universal definition of association, right?
Right.
We don't have a universal definition of dependence.
Of?
Right? So do we? We don't, right? So why we be so hard on the causality itself? Like we have all these vague notions. We mathematically define different versions of dependence, right? There's statistical dependence, there's algebraic dependence. Why don't we do the similar things for causality? Have a different version of causality depends on what system you are talking about.
No, yes, we can, this is related to a question that was done before. So we can attenuate the validity of the definition and making it less universal, let's say, like grading it, like correlation and things like this. What I'm saying is that normally the physicists and the mathematicians are used to work on fundamental things and fundamental questions. So somehow many of us tend to not to concentrate on this kind of topics, but this is an interesting solution which doesn't belong really to the nature itself of physics. But there are some fields of applied physics in which people do this. It's just I agree. It's not about the physics, the physics like the theorem, Bell theorem, this thing, everything. Absolute truth.
Hi, this is a great, really interesting discussion. And I wanted, so there's kind of two questions that I have. One is kind of clarification, maybe by way of the discussion, which is, I wonder, so I don't think I'm understanding everything, but I think one thing that kind of comes through is that when physicists talk about causality, it's kind of an unconditional causality, that, you know, event E precedes event E1 precedes E2, and that always happens, no matter the conditions. Whereas I think a lot of people in this room have a much more loose definition of causality, that if there's any time for which something changes and something, you know, then that is an example of causality, even if it only happens under certain conditions or things like that. So maybe, I think it seems like maybe there's a higher level of, there's a more restrictive definition of causality that it seems like is happening here versus a much more pragmatic one that we take on a day-to-day basis. So maybe that's, I don't know if that's true, but that's one.
No, but I agree, as I said, among the different definitions that Bertrand Russell tries in his seminal paper, as I said, among the different definitions that Bertrand Russell tries in his seminal paper, this is my favorite definition. Just it applies to a limited amount of cases, and it is a definition maybe acceptable for many, but is not really formally rigorous for a physicist, because in the end you say, well, but what is short enough? But what is but it is my favorite definition after all. So, and it is also Russell's favorite definition, but in the end is not satisfied.
One more, maybe this will just lead to more confusion. But we take, I think, generally speaking, we think of causality in a probabilistic way, because realistically, for the level at which we study it, it is probabilistic. But I wonder, again, it's a lot of like constants here, and we get this dip into the quantum realm, and I'm wondering, is there a probabilistic, quantum probabilistic definition of causality that comes out, or is the physicists kind of all are aligned on this idea of causality as being kind of like a deterministic feature of the world?
Okay, if you take the relationship in which that you want to explain through causality, examining the correlation between the final outcome of a measurement and the initially condition, the answer is yes. There is a probabilistic calculation of the outcomes of a measurement in quantum mechanics. So in this sense, there is an evolution of the system that is deterministic. And then there is the result of the measurement that is probabilistic. So this is the basic of quantum mechanics. We are not really blind, I mean, but it is probabilistic.
Yeah, the previous question really got on this, but I think we've encountered this difference between the physics conception of causality and then the conception that we use, and I think it's pretty impressive that we're the ones saying that actually physics is wrong. And so I think that, in fact, what I take away from this is to say that the potential outcomes framework that we've come up with is not foundational. It does not actually map onto some kind of ontological reality, and we're using it because it's useful. And I think we should continue to use it while it is useful, but we should not let it be the actual, our understanding of the world. And so if it ceases to become useful, or if things we could change about it to make it more useful, we should be willing to do so.
I agree completely with what you say. As I said, I don't dislike this definition. This E1, E2 definition I don't dislike. The person who introduced the problem of the causality relation between human activity and global warming, I don't remember who was. It was an American guy, yes. Okay. Stated a definition similar to this, but then in his case, this time tau was overlapping with the consequence. So somehow this makes more shaky the conclusion in a formal word. But in the end, this doesn't mean that the conclusion is wrong. It means that it is not formally consistent with a certain idea. And in the end, for example, I believe that the causal relation between anthropic activity and global warming was established by consensus, not everybody agrees. And it is still a good thing, I mean, to have it. I prefer, I mean, for example, okay, they make a consensus, they say, it's not formal, but in the doubt, there is a lot of probability, so I prefer to be prudent. Okay. So.
Question from Fabrizio.
I think it's not a question, but a further comment, also following up to what Matt was saying. Essentially, we are not really also using potential outcomes, defining really this big word causality. We are a lot more pragmatic and try and find quantities that we are eventually able to possibly estimate and also use for example, decision making. So we are essentially attaching or formulating causal effects more than causality in general by linking these potential outcomes to actual actions. Like what would happen if we were to reduce the air pollution, or what would happen if... so these type of very pragmatic questions possibly sometimes, as we know, have answers and are, I don't know, we can answer them through experiments, with data, under certain assumptions. They are not meant to essentially explain the world and actually get to the fundamental, or the foundations of knowing what a cause is. So it's a, we are moving the goalposts, say. It's too difficult to maybe understand the whole world, and so we are answering specific and formulating causal effect as specific questions that are always tied to specific hypothetical actions that we could do.
I agree. Of course, I agree, and of course, I always thought that physics. Physics answers to a limited set of questions.
We do. I mean,
but
it's very limited.
But more, I mean, yes. I mean, really, the number of questions that we answer is really, really low. I mean, if
Fabrizio, I have to say that I disagree with you because I think that there is a distinction between a definition of causality and the tools to assess causality. And what we call Rubin causal model, in your opinion, is what? What we call the Holland's paper is about defining causality and then how we establish whether a relation is causal or not. But the definition is there, is based on the comparison of counterfactual, and that is a definition. Then you may not like it or not.
They are tied to actions. They are not tied to variables like gravity or anything. They are essentially, so if you were to explain, for example, a physical law of how gravity is affecting something else, you should conceive a world where gravity is not there, or you can manipulate gravity, which is fine. But it's different from the notion of causality that I guess.
No, what I want to say, sorry.
Alessandro, I'm afraid we have just last question because then
okay, I just want to say one thing about the counterfact hypothesis. I want just to say one thing. Suppose that you have a subject that now is high fashion, multi-layer perceptron. Okay, a multi-layer perceptron. You have a network of nodes. One node is I don't know what, one neuron. You remove that neuron, and then the answer changes completely. Can you say that the cause of that answer was the neuron? No. But you can say that there is an evidence that the neuron played a relevant role in the answer. So this is different from cause-effect. It is a correlation. Okay.
So I guess for me, when you talk, when you were talking about the fundamentals of physics not being for causality, that all makes sense to me. The equations that you show are basically representing states of variables. I'll use pressure, volume, and temperature because it's easier to think about. There's a relationship there with an equal sign. But it doesn't matter what's on the left or the right. You change the state of any one of those variables, and the others will change. To say one causes the other is creating a particular constraint in that question. And then if I change pressure, then volume will change. If I change volume, pressure will change. So the fundamental principle to say that pressure causes volume eliminates the chance that volume causes pressure. So that's the fundamentals of physics, of these universal laws. And then there are other times when we come into health or into the larger world and in people where there are things that changing the state of one will change the other, but not vice versa. But physics isn't interested in those questions. It's interested in the fundamental laws where we just have these states. Would that be, is there anything stupid in what I just said?
No. What you said is right. Sometimes you can even write it in a way that many people like, with variation of this in time equal to something else, which is the clear cause-effect relation. Sometimes it happens, but not always.
Okay, so thanks a lot, and join me. Enjoy the coffee break.
Let me thank the organizer for having me organizing this on this topic, which is quite new for me. So I'm starting from something which is a little divergence about this, because we have heard of Galileo and Aristotle, and now we can have Socrates. So this is some way the motivation I started looking at fairness. So in some way, I was thinking, as a statistician, I'm a Pythagorean person, because everything is a number. And so I said, no, I want to be Socratic. And what it is Socratic machine learning? It's a Socratic machine learning for a better word. This is my opinion. So a Socratic machine learning is not a different kind of machine learning. It's the standard machine learning, but with a different philosophy that in some way is guiding the machine learner. And the idea is that, for example, you need to be aware that I know only that I know nothing. So, and this implies that I need to evaluate uncertainty and not go after accuracy as the first thing in my life, but we need to evaluate, for example, with conformal prediction of whatever, yes, we need to doubt our outputs. And another is know yourself, and in particular, know your algorithms, which means not just use them and pick up the one which is the best for that data, but know them intrinsically, when they should work and when they shouldn't, and how to use them, okay? So to be aware of that. And then the main thing is Socratic wisdom, which is the ethical responsibility of the machine learning nowadays, where artificial intelligence and machine learning are spreading in our lives. So it's very important, and here is the fairness that I will introduce you in a minute, and explainable AI. It means those class of procedure that helps us to understand how AI and machine learning algorithms are actually obtaining the predictions. And then the Socratic circles and the Socratic dialectic, which is actually what we are doing in this conference. So it's putting methods and people together with different expertise. And maybe if we exchange one another and we use something which is a mixture between a machine learning algorithm and a statistical model, and there is this fusion between us, something is going better. Anyway, so what's fairness? Fairness is the absence of a prejudice. So in statistics, we are used to have good estimators, okay? And in this way of conduct, we are actually in a worldview in which we say what you see is what you get. So statistical modeling is actually providing exactly the same amount of fairness and bias as in the population, okay, at least asymptotically, we should say. Instead, in machine learning, you can have that also the algorithms can induce some bias, okay? So for example, trees, all the tree-based algorithms can induce some bias. So this could make a worse word than the actually one. But at the same time, if we can correct this algorithm, then we can have a better word. So for instance, the other worldview is we are all equal. So we can have an algorithm that it is less accurate than the standard one, but that it actually induces some reduction in the bias and discrimination in the population. So the main questions that are there is how we define fairness. There are tens and tens of definitions, and every single application needs a specific definition of fairness. And once I know how they can define it, I need to measure it properly, possibly with its uncertainty. And when I can assess if an algorithm is discriminating, what can I do? How can I modify my algorithms to improve this situation? So I'm just giving you a few definitions. So Y is the response that I want to predict. X is a set of covariates. Y hat is my classifier. Usually fairness is seen in a classifier situation, but you can define also with continuous outcomes. And S is a sensitive attribute, a sensitive characteristics. For example, it's gender, age, it's race, and so on. And you don't want that your prediction discriminate these people. So the first simple way to define fairness is statistical parity, which is also called, I don't know why, demographic parity. And it tells that our prediction should be independent on this sensitive attribute, or marginally or conditionally to something. This is not so easy because define something new is, and unfortunately, because of the famous and beloved Simpson paradox, you can be fair in every subgroup of your population and unfair on the marginal population or vice versa. So it's very strange things. So instead, equalized odds is sort of being fair when you are wrong. So it's conditionally on the outcome. The prediction is independent of the sensitive attribute. And then there is the counterfactor. I think you are mostly in this part, where actually a decision is made as a consequence of the prediction. And so we want that this decision is independent of the sensitive attribute, conditional on the counterfactual, the potential outcomes. So I'm not an expert so much, but here there are three very different experts. I like that they are with a very different background. So we have Christine Bennett from the RPI. She is a computer scientist and she's a professor in mathematical sciences. And of course, her interest is AI, machine learning, fairness, and so on. Then Silvia Chiappa, she is a researcher in machine learning at Google DeepMind. So she also is interested in causality, so someone you can know her. And the same is for Kosuke Imai, that for sure you know. He is professor at Harvard, and he has a lot of works in causality, computational social sciences, and also fairness. So I think the definition of counterfactual fairness is actually due to him. So I finish and giving the floor to them. Come si fa?
Can you hear me? Okay, I'm going to use the mic because maybe you're having trouble hearing me before.
What is yours?
It's at the top. It's called, oh, where'd it go? Not that one. It says Bennett somewhere. You just downloaded it this morning.
Roundtable 4. Okay.
So put it in presentation mode.
I don't know Windows, sorry. Where is the presentation?
So,
I will speak that. Sorry, I'm a Mac person.
Okay, well, first off, I'd like to thank Anna for inviting me. Like I said, I am not a causality researcher, and I appreciate you all so much because I use all of your work. So thank you for making it out there so I don't have to recreate the wheel and I can leverage it. And I got into this because I do a lot of work in health and health informatics, and I was doing a contract with IBM, and I worked with this doctor, and he said, we're doing cohorts, ontologies for representing clinical trial cohorts. And they're like, well, let's do something useful. Can you tell me if the trial is fair? I'm like, okay, what does that mean? So unfortunately, I've had my human subjects training, and they teach me that we should worry about justice. And that basically means that it's fair and equitable of the benefits and risk of the trial. We want to make sure that no subgroup is disproportionately disadvantaged or gets all the advantages, right? So that's like justice, so you've got to be within reasonable parameters. And then there's the concept of equity, if you read papers about this. And basically what it's saying is that the clinical trial population should represent the people who are going to use the treatment, right? So there should be a match, if you're talking about diabetics in the United States, you want that population. You don't want to care about the race and ethnicity of the whole population. You care about that. But it turns out we're not very good at clinical trials that are fair yet. It's a goal in progress. There's many examples of health inequities. I just grabbed one here. This one says that black patients in a study were 54% more likely to develop dementia. But there was a study that also said they're only in 2% of clinical trials. So clearly they're underrepresented, right? This is not fair, right? They might not, maybe there's different, for whatever reasons that are the causal mechanisms, there's some kind of relationship between your ethnicity and your health status, and that, that influences the drugs and your treatment. So this is my idealized view. I have not seen a DAG in the entire conference, so forgive me if I've done something wrong. But okay, but here's a real simple one. This is a simple clinical trial in my mind. Hopefully I've got it right. You have this randomized clinical trial. We have this target population, which is these people I want to hit. And I have some covariates that influence the outcomes, and I have whether this person gets to be in the trial. Because to be fair, I got to make sure the people who get in the trial match their target population. This is supposed to be random, and who gets the treatment, that's supposed to be random, right? So, okay, that's a fair one. But what happens in practice? Okay, then you can just, do the treatment effect, and it represents the population one for your target without doing anything fancy, right? That's the idea of a good clinical trial, and you spend a lot of time trying to justify this when you design a clinical trial. So, the key idea is that the random sample, the RCT randomly samples the subjects from the target population, both in the treatment control, right? And so it's all the same distribution. But in reality, this is not what happens. We know that for whatever reason, there's covariates that matter for the outcome that influence who gets in the trial and maybe also their treatment or not, right? So I'm going to use like a shorthand. And like I said, forgive me, I'm not a causal person all the time. So I'm just going to call equity. I'm going to call it when you mess up this argument. Equity means that you're not getting a trial population that's representative of your target, right? And I'm going to call propensity that your treatment and controls match. And I'm using propensity like Kleenex. I don't mean you have to use propensity, but something like that, right? Okay, so, but the important thing is that once this covariate influences my subject in treatment, then it's no longer a random sample of the target, and I have to do some other work, which you guys all do all the time, to make sure I get the target average treatment effect. I think this is animated, yeah. The estimate's not going to be correct, right, unless I do some extra work to, and I'm not going to go over all the techniques. You all know way more about that than I do. So, anyways. Okay, so when I approach a new problem, I always like to draw pictures of the data. I've done that in many, many fields, and people are like, wow, I never thought of that, you know. So the first thing I like to do is to find a good metric. So I've done work in ML fairness. So there's this metric called disparate impact, which measures statistical parity. And basically, what I think, what we're looking for is the probability that you get in the trial is the same regardless of your covariance. And that's a fair trial, right? So we're using, if you do some math, I came up with this log disparity, which is based on disparate impact, which is the ratio of the odds of being in the trial and the odds of being in the target for that particular subpopulation. And you could look at any subpopulation you want. You can do it with respect to sensitive attributes like age or whatever. Here I have in respect to gender, age, ethnicity, and so education or something like this. And you can look at those and you can see how well does it match. So what we do in practice is we go out to external data sets, in this case I use NHANES, to estimate the target population rates for all the subgroups and all the combinations and all the levels. And then we compare what was in the trial to this target. And the target is something, you know, ethically you have to define. Right? So I've decided my target is people with hypertension, and I'm evaluating the ACCORD trial. And you can see, like the colors, we worked out the colors. We want to make something very visual that you can easily see what's going on. And you can see, well, we're a little short on females, that's red. If you have teal, it means you're statistically no difference or within a range that would be considered tolerable. And then you can see like red, dark red here means like Hispanic women were just missing from the trials. There was, oh, I know, women 1844, they're not even in the trials at all. And we saw that men are pretty well, and middle-aged men are well, but not Hispanic ones. And we have good representation, let's say, of women, middle-aged women, and people. So this is a way for you to examine your trial and see what's going on. So you could use this like for a report card for a trial, or maybe if you souped it up a little bit and you were doing meta-analysis, you could do a report card for the equity of your meta-analysis, and you can compute these quantities and do statistical tests and stuff and see how you're doing with matching your trial. So that's, and okay, now that we have this metric, you can do all kinds of fun with that. So, by the way, my background is originally operations research and optimization, so I have to do optimization. So a big problem is you have to do an enrollment planning, right? You have to come up with a plan, and NIH makes you do this, and you have to put in race, ethnicity, and gender, and age, and look at the combinations, and say, I want, 100 of this, and 200 of that, or whatever. Where does that come from? Well, so we made a tool to help people make fair trials. So it uses optimization, multi-objective, it's called goal programming. So you have these targets that you've determined from your target population that you want to hit for specific subgroups, and then you make an optimization problem that balances like, well, you want to make sure you don't disadvantage, you want to have justice, that means you have to be within a certain range or we would be unhappy. And you want to match the distribution, that's kind of overall you want to match, but also maybe you want to, it's a multi-site trial, and you want to make a fair trial that's also that's inexpensive, right? That makes good use of people. So for instance, you could use additional data about the sites, and you might look at the demographics of the sites. What kind of people are there? So you want to make it so if you're recruiting at those sites, that if you get so much from this side and so much for that side, you might get a better match to your target than, so it helps you decide where should you put your sites. So we gather information like from New York State about where trial sites could be and use that. So, and it's a multi-objective, so you can help you save costs, it can help you have justice, it can help you have equity, and be more efficient in your recruiting. So this is a tool for doing that. And this is like, teal means, oh, you're great, red means this is the sprint trial, which was diabetics, and you can see it's not equitable. At least not with respect to this target population, which was people in the United States. Okay, so the next question we're looking at, which a lot of people work here, and so I'm not going to try to review this, but what if you want to add real-world data? So maybe you have rare disease, it's very hard to recruit people, or you wanted to have more power efficiency. I'm sure you know lots of reasons, like the talks we heard this morning about that from Elizabeth Stewart. So what you do is you make a hybrid synthetic population, and you should worry about both arcs. So when you do observational data, most of the methods I see, they only worry about if the treatment matches the control, which I will call propensity. But you really should worry about equity at the same time. So what we did in this study is we designed methods that look at propensity and equity at the same time. And if you just do propensity and you just do equity, you're not going to get the job done, right? You need methods that combine both. And you have made many beautiful methods for propensity and equity that we can use for this type of analysis, but the point is you need to do both. And we've made a framework for research in equitable synthetic control arms. It's called FRESCA, and it takes clinical trial data and observational data from NHANES, and you can simulate trials that use external data. And it's all public, I mean, kind of public, if you get permission from BioLink to use the data, but you know, it's free. So we have this whole simulation framework for looking at algorithms that combine propensity and equity. Okay, and this is going to estimate the target treatment effect, right? But now you can use this external data and get better estimates using less data that are more equitable. Okay, so then I'm an AI person, I do large language models. So you guys have left this in the room. When you go use your stuff, you have to pick the covariance. If you're going to do propensity matching, you have to decide how to match. That is not an easy problem. I've gone to health companies and they asked me to evaluate some study of diabetes interventions, and you know, picking out what to pick for the covariates to match on and stuff is hard. So it turns out we got really good data then, because every study has a table 1, and basically something like the table 1 is in clinicaltrials.gov for hundreds of thousands of studies. So we had the idea of making an AI system that you feed in what your trial is, what's your outcome, you know, what are your exclusionary criteria, and it will suggest the baseline descriptors. That's what they're called in clinicaltrials.gov. They're the covariance that you want to measure to make sure you have a nice trial, right? Both in matching the treatment and control and also possibly for equity too. So we have this new benchmark. It just came out. And so it uses LLMs to predict, and it actually does a pretty good job. And you can imagine it's pretty hard to do this because this is only with zero shot. Zero shot means like we just prompted. We haven't done any fine tuning. I'm sure it'll get much better. But it will suggest a list of descriptors for the trial, and then we'll use another LLM to evaluate it. Because the problem of evaluation is hard because it might say BMI, and then the system might say body mass index, and you have to know that's the same. Or it might say Charleston comorbidity index or X-Hauser index, and well, they're not quite the same, but they pretty much measure a similar thing, so they're kind of substitutable. So we asked the LLM, does this stuff match? And it produces a match, so we can evaluate. So we use one to suggest and one to evaluate. So this is a new one, and the results are very promising, and we're improving it all the time. Like now we do retrieval augmented generation where it gets relevant clinical trials and then feeds that to the LLM, so we'll have relevant predictions. And then the other fun thing you can do is you can ask it to explain itself. Like, why did you suggest the comorbidity index? And you can ask for sites, it will explain itself. So this is a great tool because, you know, people who want to apply your methods, they don't have PhDs all the time, right? They're not as smart as you, or they don't have the experiences, and they might be in the domain. So you want to make tools that let them do stuff. Okay, so in the end, here's my vision. I think we can make AI agents to remove the barriers for using all your stuff that you guys are inventing, right? So we can help practitioners deploy state-of-the-art causality methods for assessment and design of clinical trials, for execution of them, and analyzing the results, right? You can do this, and I think this is completely feasible. And you break it up into little pieces, and you solve different pieces at a time. So I've already showed you one place that we could do we could do this assessment of suggest features. But like to do my population analysis for target, that's kind of a pain in the neck, because you have to go analyze another data set. But hey, if you're always using the same data sets like NHANES or something, I could write you a system that generates the code and analyzes NHANES, and you specify the details and it would pump it out. It's pretty dang good at code generation. It's getting better all the time. So we could actually do the analysis for you on the data. And you could use it to apply your methods where you needed all this source information, and it would help you suggest models, help you do the code, and help you analyze it. So it's a way to remove this barrier for do this. I have another example here working with Mount Sinai, and they have this problem of it's called disrupt. They want to get more diverse people into clinical trials. And the problem is they never get access to the trials because the doctor never says, have you considered a clinical trial? Like for cancer trials, like white people are really good at finding them, but many groups don't because of the types of care they receive. So they want an LLM to go read the clinical notes and look at the data to go find these people at critical decision points in their care and then suggest to them. They actually will do a notification to the doctor to say, hey, have you thought about a clinical trial? Here's the information. And, or they could send it even to the patients. Hey, have you thought about a clinical trial? Here's some you might want to consider. We've matched you up with some. So, and also you could do this in, I know when I do observational studies, I never knew where to pick the index events. But basically you want to match that these are same people in their clinical course of their treatment at the same time, at the same decision point. And that would be a much better match. So there, you can imagine if you could do that, you could use that for lots of things. And of course you could do it to get your fair target population treatment effect and analysis. So I know I talk fast, but we're a little behind and it's the last meeting. Yeah. So there you go.
Can you hear me? Yes, I can hear myself. I'll try with this one. So first of all, thanks, Anna, for inviting me, and also Fabrizio, and also the organizer for putting up such a great event. So in this talk, I'd like to give you a little bit of a taste of how graph-based statistical causality can be used in fairness. And I have to admit that the last 7 years of my research I've been using graph-based statistical causality to solve all sorts of problems from fairness, which I will cover today, and I will focus only on the classic MLs on prediction and regression, but we have work also on decision-making and more recently on fairness for foundation models. Also in the focus of the causal intelligence team, which is about reasoning in foundation models, and also in sequential decision-making frameworks such as Bandit, Bayesian optimization adapted to learning of policies and reinforcement learning, where really graph-based statistical causality can be leveraged by, in order to make these frameworks much more efficient. And so by using the do calculus or the extension, the sigma calculus, or a lot of new work about exploiting redundancies, we can leverage offline data and reduce the action space. So, but this is a little bit like to say that my kind of history and perhaps unlike some of the people here today is about the graph-based approach to statistical causality, also partially coming from Phil David lab where I spent some time and other labs. So if I have to think about statistical causality, I would like, in my mind, distinguish two main areas, the one in which we want to estimate causal effects and counterfactuals, and we want to even establish whether a variable has an influence on another variable. And the other big area of trying to learn policy, so trying to find the perfect or a good assignment of interventions. And I will focus only on the first part here today, although, as I said, we have worked also on fairness in policy design. And we'll also focus on the observational setting in which we assume that we have given data that are collected without the possibility to set values of some variables, so we are not able to manipulate or perform interventions. And in there, causal inference is these disciplines that tries to express the desired interventional distributions as functional of the observational distribution, such that we can then estimate desired quantity from the data that we have at hand. Now, the graphical representation of cause and effect relationship is very useful for facilitating this task of expressing desired interventional distributions as functional of observational distribution. And in particular, the basic graph that is in use, but there are a lot of extensions, is the so-called causal Bayesian network, which is a semantic extension of causal Bayesian network in which an edge has a causal meaning. So here, for example, E, a random variable, is a random variable that has direct influence, causal influence on X. And associated to each node in the causal Bayesian network is a conditional distribution that is really given a causal meaning. In here, for example, X is associated, the conditional distribution of X given E, which dictate the way the variable X behaves as a function of the parents or the direct cause E. The joint distribution of all the system is now then simply the product of this causal mechanism. And then we can represent interventions in the system with like the classic do intervention, in which we replace the original mechanism with a delta function that expressed that we are going to set the value of X, for example, to small x. And this is one type of intervention that I will focus on the talk, but there are more general type of interventions called soft intervention, in which we replace the original mechanism with another one, a different conditional distribution, in which we can even change the parents. For example, in this graph here, X, with respect to the previous graph, as a new parent, which is C. I'll say I will focus though on the hard intervention to trying to introduce the concept of path-specific influence. Yes, sorry, there are a lot of literature from Jutea Perl. I don't know if that's why you are commenting on this. So basically, we can say that the main goal of using the graph-based statistical causality is to differentiate statistical dependencies from causal influence. For example, here A on Y as influences through the causal paths that are depicted in red, but there is also spurious correlation through a non-causal path via the variable C. And so the goal of really causal inference is to estimate that causal influence of A on Y, which I denote with a strange symbol, is a little bit different from what Perl uses the due to just emphasize that we are talking about different distribution. It's a distribution of Y given A when we ever remove the spurious path. Now, though, we can go much further in using this machinery and think about different art interventions. Before that, I like to say that we can summarize this process of intervention by going from the original graph in which we remove the incoming edges into like a summary graph in which we just remove the node A, and we replace the conditional distributions associated to Y and D, which conditional distribution where we have set the value of A to small a, so the intervention value, right? This is a summary, and then we can compute the causal influence that A has on Y simply by marginalizing out the remaining variable. Of course, this is a very simple case, but just to give you an idea of how to perform this operation of estimating causal influence. And as I was saying, you can go much further and think of performing different art intervention on different emerging links from A. For example, in this case, I have set A to small a in the path that is mediated by D, and I have set A to small by a along the direct path from A to Y. And we can represent and summarize this type of path-specific intervention by going through a graph in which, again, we remove A and we set the conditional distributions associated to Y and D with ones in which we have set the value of A to small a bar and small bar A and to small a respectively. And then we can compute the quantity that I denoted the causal influence of A on Y with this different art intervention simply by marginalizing out C and D from here. So now, like, we can introduce the potential outcome, so this new random variable that simply has the distribution, the conditional distribution that I was talking about earlier, right? And similarly, for the path-specific type of intervention, we can define a path-specific potential outcome random variable, which has similar distribution equal to the conditional distribution of Y given A, where we set A to different values along different paths. And then, as we normally compute the average treatment effect that measures the difference in causal influence when we set A to a small bar A or to small a, we can do something a bit more sophisticated and compute what is called a path-specific effect when I replace the first term in the average treatment effect with a more complex one. I think this is the pointer, yes, a more complex one, which is the expectation of the path-specific potential outcome random variable. And basically, if you try to think about this difference, we are measuring the difference of causal influence when A is set to different values along the mediating or mediator, the path mediated by D, and sorry, is kept fixed to small a, and we set A to different value along this path, right? This is what is done here, and the meaning is that of this is that we leave A to small a along D, and but we set it to small bar A along the direct path, while here we kept A to small bar A in both paths. So basically, this is kind of measuring a little bit what's happening along this direct path when we change different values of A, right? It's a kind of a measure of a direct effect. And that's extremely useful for fairness. Like this formalism enables you to describe different fairness scenarios and also to measure some path-specific effects. It also allows, that's what we have done, to develop an audit for fair prediction models. To just to give you an idea how the machinery can be used to describe different unfairness scenarios, I'll discuss the famous Berkeley alleged sex bias cases where female applicants were rejected more often, and it turned out that the reason for that was that they were applying to departments that were more competitive. So from the viewpoint of the college, you might think that actually it's fair to reject women more often, as the college didn't impose women to apply for more competitive departments. It would be, the question is maybe if two individuals with the same qualification and applying to the same department, one male and one female, would be treated differently. In that case, that means that there is a kind of more direct influence than the gender has on college admission that is considered unfair. We could also give a different meaning to and say, oh, perhaps from the point of view of society, actually it's unfair that women apply to those departments. Maybe there was some type of pressure, and so we could consider this path also unfair. So there are all sorts of scenarios that we can depict. Here I just show 3 cases. Just to give you an idea that what you can do with this graphical representation, you can, even very roughly, because of course it's a bit rough to deem a path as fair or unfair in this way, but you can start to perhaps give more formalism to the problem and start to tease apart effect that you would really like to remove from the system or you won't like to test in the system. Yeah, so basically here just to give you an idea of the things that I've discussed before, like I added an extra edge to make the example a bit more interesting, in which there is also an effect of gender on qualification. We could decide that, and by no means that I'm not saying this is the correct graph or is correct to deem this path as fair or not fair, but we could, if we agree that this path it is deemed fair and we want to measure the unfairness along only this path, what we could do is to compute the path-specific potential outcome, as I showed before, to measure the difference in expectation when we set A to different value. In this case, a value would indicate being female and another value would indicate being male. We can go even further and condition on a specific individual to compute, for example, what would have happened to a female individual that was rejected, was not admitted, if she was male along a certain path, to try to understand whether there was discrimination against that particular individual. We can go further. This was about really formalizing and measuring unfairness. I want to kind of conclude by briefly describing the possibility to also develop fair prediction models in which and what we can do is to try to have, if we have a data set with a causal graph, that the underlying causal graph as the one depicted here, what we can do is to train a model that really trying to kind of learn the conditional distributions attached to this graph. And then what we can do is a deployment time. So we train the model on this unfair data set, and deploy time when we have a new individual, we can assign to the individual as outcome, not the outcome that the model would give, the trained model would give, but the path-specific potential outcome. So what the model would have given if we were to set, for example, a female candidate male along the unfair path. And yeah, I just want to say that I described this as being very simple. All this is quite complex, so we deploy for that, like, got inspiration from the machinery of the methodology of Judea Pearl, but I had to input a lot of machine learning into this, trying to make the model quite flexible to different type of distributions, and also to ensure that some properties were maintained. For example, that the latent variables or in this action-abduction prediction method of Judea Pearl would remain independent of the sensitive attribute. So for that, we have to apply some MMD-like methodologies to make that, and we also had to apply some approximation technique from variational inference to make sure that we could handle like untractable model. And with that, I think, yes, I just give you a very high, I think, a level overview of how fairness can be used in this. And I want to conclude that this is just the beginning. We also did some work on policy design for learning optimal policies from observational data. And, but that's a very, very kind of unexplored topic in research, and the one that is now very pressing, namely like dealing with fairness and robustness in systems like LLMs, or these systems that are trained not in one go but are fine-tuned, is pretty much unexplored, so there is a lot of work to do in there. So thank you very much for the attention.
Okay. Yeah, so thank you for inviting me, and it's always wonderful to come here, and it's a wonderful symposium. I've been thinking a lot about different issues. So I think Sylvia gave a sort of theoretical overview of what the fairness is. I'm going to do the opposite, which is to go to a very specific case to see if I can balance a little bit. Okay, so I'm going to focus on the question of now we have this AI or data-driven algorithms are everywhere, and but in the field where I study, still the humans are making many decisions. So we haven't, not yet at least, outsourced high-stakes decisions to AI or algorithms. Okay, and this is actually true even when the human. We know as a social scientist, the human decisions can be very suboptimal, and they can be quite biased. You can think about why is that the case. We probably want to have some accountability, maybe, to hold somebody accountable rather than something accountable. Okay, but I'm not a philosopher, so I'm not going to talk about what we should do. But instead, I'm going to focus on this AI-assisted or maybe algorithm-assisted human decision-making. As a social scientist, I'm interested in the interaction between the two. So more specifically, I'm interested in humans making decisions with the help of AI or algorithmic recommendations. Okay? So we do this all the time. We do shopping with the algorithm help and doctors, judges. Okay? And I'm going to focus on project I've been involved in last, I think, 5-6 years. It's been a long time. To give some context, but before that, I want to focus that some of the key questions that I think are important is how do these algorithmic recommendations influence human decisions, and does it actually help us make better decisions, and maybe does it improve the fairness of the human decision? I think there's a lot of studies that look at the accuracy of fairness of the recommendation themselves, the algorithms themselves. They are a little easier to study, in my opinion. It's just the mathematical objects. Humans are totally unpredictable, unreliable, a lot of heterogeneity. Okay, so I sort of want to encourage you to sort of think about how the humans interact with the algorithm. In particular, I don't think we know much about how the AI bias or algorithmic bias interact with the human bias. Right, so the particular case I'm going to tell you very briefly is something called pre-trial public safety assessment. Okay, so this is basically the algorithmic recommendation used in the US criminal justice system. Actually, the particular instrument I'm going to talk about is used in more than 25 states. So here, at the first appearance hearing, so you get arrested, go to the court, and the judge has to make decisions. They have to decide whether to release an arrestee pending disposition of criminal charges. So you haven't been charged yet, you're just got arrested. You could be innocent. And if they decide to release you, under what conditions? So there might be a monitoring condition of bail. Okay, so the goal is to avoid the unnecessary incarceration, because you could be innocent, while preserving public safety. So if you're deemed to be a threat to the public, the judge wouldn't want to release you. Okay, so judges are required to consider 3 risk factors by law. Arrestee may fail to appear in court, so they might run away and may never come back to the court, or they may engage in a new criminal activity while being released. And particularly, they are worried about the violent criminal activity. Okay? So PSA, or public safety assessment, is basically the algorithmic recommendation to judges. And it classifies arrestees, gives numerical assignment based on these risks. Okay? So we run this somewhat crazy field experiment. And I'm going to show you quickly the results from the Dane County, Wisconsin, US. And so here, the PSA is weighted indices of 10 factors. Fortunately, or unfortunately, age is the only single demographic factor that's being used. Okay? There are 9 factors drawn from essentially criminal history, prior convictions or prior FDA. There's 3 scores. There's 2 separate ordinal 6-point scores for FDA, failure to appear, and NCA, new criminal activity. And then there's a 1 binary score for violent criminal activity. It's like a prediction of how likely you are to engage in these negative activities. And then they put all those together and then give an aggregate recommendation to the judge. So signature bond here means that you can just sign a piece of paper and you're free to go. So it's basically release. And the small or large cash bond bail is about like $1,000. That's sort of the threshold that they are considering in this jurisdiction. So it's a very petty crimes that they use this for. So there's no like detain for without any condition. Judges may have other information that I don't have access to. So there may be affidavit by a police officer. There may be a defense attorney present. The judge may talk to them, etc. So the field experiment that we were fortunate to do is to randomize the provision. So for some cases, the judge receives this recommendation, and then the other cases, they just don't get to see it. Okay? So here's the actual piece of paper the judge sees, and you can sort of see there's 3 scores. So there's a binary score for the violent criminal activity, and then 6-point scale score for the new criminal activity and failure to appear. And judge actually sees all the input that goes into this algorithm. So the algorithm is just like weighting different factors differently. Here's the overall recommendation. In this case, the algorithm recommends that the person should be released. So question you might ask is, like, does the judge agree with these recommendations? So here's the actual judge decision from the data, and then here's the recommendation. So this is a case where the judge don't see the actual recommendation, but we can calculate the recommendation itself, so you can compare what happened in terms of agreement. And you sort of see that about more than 60% of the case, they agree, like 70%. And then, but there's still a substantial amount of disagreement And the algorithm tend to be a little bit harsher than the human judge in this particular case. So here, the comparison, when the human actually sees the recommendation, how does that agreement look like? It's a little bit higher. So it seems that humans are a little bit influenced by the algorithm, but there's still substantial agreement. And again, the recommendation is a little harsher. Okay. So experimental design, I think what's nice about this is that we can randomize the provision of the recommendation, and we can make this exclusion restriction. So the recommendation only affects the outcome through the human decision. So it turns out that with this exclusion restriction, you can learn a lot about how these systems, decision-making systems, biases the decision. Okay. So just quick, so framework only. So we basically think about like this classification system. So trying to evaluate like human alone decision, human plus recommendation decision, or maybe you want to know like what would happen if you just let the recommendation decide to get rid of the human or whatsoever. Okay, so here's like a 2 by 2, and interesting thing, we're going to look at the potential outcome when you release someone. So what would happen if someone is released? That's what we're trying to predict. In fact, the PSA is that's what's supposed to be predicted. Okay? So here, that the positive decision is cash bail. I mean, not positive in the normative sense, obviously. Negative decision is release, signature bond. And then the outcome, for example, positive is NCA, actually person getting arrested for the new criminal activity, and then negative is no new and NCA. So here, right decision, you can think is that if someone is not going to commit a crime, you should release the person. So that's true negative. If someone is going to commit a crime, maybe you should give a cash bail. So you can think of false positive as unnecessary cash bail. False negative is a signature bond, releasing someone followed by NCA. And then you can assign the loss to each of these cases, and then think about like classification risk in the classical sort of statistical decision framework. So it's a function of false negative proportion and false positive proportion. And the misclassification is when you weight the two factors equally. That's misclassification. Okay, so this is just normalizing the loss. All right. So it turns out that we cannot identify the risk of each system, obviously, because the decision itself isn't random. Who knows why the human judge is making certain decisions? But it turns out that you can point identify the risk difference between human and human plus recommendation case. And also, you can bound the risk difference between human and AI alone, or PSA alone, even though you didn't have an experimental arm that just completely outsources it to the algorithmic recommendation. And then bounds are actually like, informative in this case. All right, so just a quick results. So here I'm showing you the impact of PSA, and positive number means PSA making things worse. The misclassification rate, false negative proportion, false positive proportion, and this is comparing human with PSA. So PSA is not maybe slightly harming the decision, making more making humans make more mistakes, but essentially it's like not much effect. Okay? But if you let the PSA decide, like get rid of the human judge, in this particular case, you start seeing like actually PSA is a lot worse in terms of misclassification rate, in particular non-white RSTs. So basically, like these algorithms tend to be harsher for non-white RSTs compared to the human judge. So you can see the false positive proportion is actually statistically significantly higher for the PSA alone decision compared to the human alone decision. Okay? So they will be giving unnecessary cash bail, giving a cash bail to someone who will not commit a crime if they are released. Okay? So you can sort of evaluate this way. And in fact, this was like just a PSA, but it could be anything. Like we're actually, just for the sake of it, asking large language models to see like whether they want to reduce. And yeah, so that's sort of the kind of thing I'm interested in. So I think we should recognize that humans still make most of high-stakes decisions. So we need to examine how these AI or algorithmic recommendation affects human decisions. And the causality is essential, right? Like when the human makes a decision, there's a lot of selection bias and things that come in. Thinking about decisions affecting people, so that's also where the causality becomes important. So in this work, we we propose this methodological framework of experimentally evaluating, like before deploying these algorithms widely in the world, and then evaluating like different algorithms, how they affect different groups of people. And for this particular case, we found that PSA recommendation doesn't really help much, and if you outsource it to the PSA recommendation, it will be worse in terms of classification performance, especially for the minority groups. Thank you.
Very interesting talks. My questions are for Koske talk. So one thing is, first of all, I think the two errors are different, right? So one might think that false positive is worse than false negative, right? So have you considered like giving different weights to the two? And then second, the algorithm could be adjusted to actually mitigate the probability of making false positive, right? While the humans a bit less, right?
Yeah. So that's a great question. So loss function. Loss is something that decision maker or maybe the public in general, the society in general has to decide. One thing you can. So I didn't feel comfortable picking. False positive is twice as bad as false negatives as individual. But one thing you can do is like, how big the loss for the false positive has to be in order to start preferring incorporating this system. So you can do this by sort of standard statistical hypothesis testing framework and then inverting to see like how big the loss can be to tolerate some of those false positives if you really care about false negatives. So that's one thing you can do. And then the second question, what was the second question? Sorry.
So the algorithm, you can adjust the algorithm.
So there's another thing we've in the paper. If you're interested, you can look at the paper. We basically like try to think about like when the human should follow the algorithm, in order to reduce the risk. Obviously, that depends on what the loss is. But so what we find in general is that this algorithm is only useful when they make a very extreme, risk score is like highest. That's the only time the human can potentially benefit from following the algorithm, where in other cases you should just ignore. But of course, this is it's actually single judge, so don't Google the judge's name. So it depends. Obviously depends on the different judge. So you can't really generalize this result to the entire population.
A question for Dr. Chiappa. So this work seems closely related to that of Razia Anabi and Ilya Spitzer. Are you familiar with this work? And are these notions of fairness and fair prediction? Could you say something about how they compare?
Actually, this work was inspired by their paper. I think one thing where that distinguishes the path-specific counterfactual fairness predictor from that work is this, first of all, this idea of trying to learn so in their work, what they were trying to do were to train a classifier to reduce the path-specific effect So they were changing the training procedure. I thought that could be a little bit risky in the sense that you might end up push some of the influences along other paths by doing that. And we have a follow-up paper exactly on this problem. So that's why in the path-specific counterfactual fairness work, I rather learn the unfair model first and then modify the outcome later, so that I tried, to learn the data generating mechanism as faithfully as possible, and then change the outcome in a post-hoc. And the second difference is that their work is reducing path-specific effects, so it's not necessarily working at the individual level, but it's just looking at, on average, to reduce that effect, while in the path-specific counterfactual fairness approach, you can assign, it is an individual level type of counterfactual that you are after, so rather than a group level predictor. So these are the two main differences.
So thanks, Anna, for a very interesting session. I also have a question for Sylvia. So regarding your idea of using the interventional distribution, I like that because it's also something I use. Then you went through the potential outcome framework. So the question is that needed, or is just convenience, or could you do it directly through the an intervention effect directly on the distribution? That's the first question. And the second one, you had a rather stylized example. So having a fixed graph, in that case, is reasonable. I'm thinking of situations where you might have more variables, so having a fixed graph is not quite amenable. So you might have just an idea of a partial graph. So do you have any experiments in which you had an unknown or partially known graph yet you can deal with?
Okay, these are a great question, the second one. And the first, I do need to introduce the potential outcome because the kind of quantity that you have to define, I don't want to go into the details, but it's all the work of Ilya Pfister that on this path-specific potential outcome that, so it wasn't a choice. But I think it's a good example of a combination between the potential outcome framework and the other, that I never see them as totally separate, so, but I think they can complement each other, and this is one is, I think, a great example. And on the second question, I have admittedly only worked with the fixed graph that I always question myself as well, and I know of some work that consider the effect of like graph misspecification from Ricardo Silva and co-authors. But yeah, in this work that I will always assume that we start with that big assumption that the graph is well specified. Thank you for the question.
I want to say something about this talk. I think it's really interesting. We are starting to talk about these topics, but I think we are still missing a lot because I think statisticians, engineers are not equipped with the knowledge to fully understand ethics and economics, all these topics in detail. And I think that talking about ethics and justice as a conditional independence is quite reductive. And I mean, if Amartya Sen could have done, I would have not wasted a lot of time to write a huge book. And there are very different opinions, like from a religious person, a Marxist, utilitarian. There are several schools of thought. So I think the first start could be like try to have different definitions that are contradictory and try to use them. This could be our first start. But I still think we have much to do, and
we are not even close to scraping the problem. And it's not just about also something, ethics is also something that goes also beyond predictions. So there are some issues also related to data collection, control over the process. So it's even bigger than that. Sorry. So I think it's even bigger than this kind of prediction problem, the ethics involved. But even in those scenarios, I think having different definition of fairness is the base minimum to start. Yeah.
So I think
I don't have, it's not addressing to anybody in particular. Anybody who wants to answer.
Well, I would say that in machine learning, I think they need a more expansive definition of fairness because they kind of artificially say that you have binary sensitive attributes and usually a single thing, and that's not very realistic at all. So I don't know if anybody can hear me. No? Okay, well, I'll say it again. I think in machine learning, they need better definitions of fairness. They're very simplified. They're binary, one sensitive attribute and alone. So they could use that input.
Yeah, maybe I can comment on this. Like, I fully agree. It's just the beginning, and that's a little bit what I alluded at the end of the talk. And I think historically, like we look at the history of fairness in machine learning, it is quite a new field, and it did focus a lot on classification and on simple settings like the binary. And unfortunately, that we are still using those, like the concept of a methodology, the methodologies that were developed there, and trying to think that they, how to use them in more complex setting. We are still super far away. That's why I'm saying like 80% of maybe the community would need to work on this. I think what we're trying to do to show with our work is also to highlight to the community the need to really take the problem seriously from a methodological viewpoint, trying to separate it from the fact that this topic is really indeed an interdisciplinary topic. So yeah, we are fully aware of that, and I collaborated with social scientists at the Mind on some of this work. Yeah, what to say, like as we lack, unfortunately, we still use those simplest definition also because the community is still quite focusing on that simple setting of classification, but society and like the community has moved much beyond that, and we have these complex systems. We don't know much. We've made a lot of progress, but we still know little how to solve these issues in these systems.
Yeah, I think there are different notions of fairness, and I don't think you can say one is right or another is wrong. But I think one thing is important is we may care about this type of research because these decisions, algorithms affect people's lives. So it's important to think about what's the causal effect of on these people's behavior and lives. So.
Question for Kosuke. So I understand that in the specific case you have studied, you want to study whether it is fair, this PSA, but have you thought about doing your own prediction, your own algorithm, and to test whether your preferred, I mean, using, I don't know, machine learning or whatever to give a different algorithm to the judge, and what is the state of the art in cases in which one wants to provide his or her own algorithm to a decision maker, which variable should be included in the algorithm?
Right, yeah, that's a good question. So we're currently in negotiation process of letting us develop the algorithm that they can actually use. Because one of the things that these algorithms, the performance is bad is because it's often based on a national database. So it doesn't have a localized context and information. And I think that's why like, a judge can sometimes outperform, partly because the judge knows, you know, so there's a lot more information the judge has. So we are trying to, actually in Las Vegas, where there's lots of petty crimes, convince the court to let us develop using more expansive database, so that, you know, and then using some of these risk framework to, you know, keep some safeguard so that actually the algorithm is helping the human. But we'll see, it's going to be a long process. So. But I think the evaluation framework is useful. Once you can evaluate, then you can try to optimize those evaluation metrics.
I just had a kind of question about clinical trials that maybe is also connected broader to sort of thinking about a consequentialist perspective on fairness and perhaps how statistical theory is helpful there. So I was thinking one thing that sometimes happens is that we do oversampling, right? If we want to actually have relatively precise estimates for a small population, we need to sort of upsample them if those estimates are going to be good, which would mean that they're sort of actually should be overrepresented in the clinical trial, not proportionally, if we want to enable subgroup analyses. And I was wondering how you thought about that in your work, and then also more generally that suggests a role for actually just really basic statistical theory in reasoning about the consequences, like downstream consequences, because without sort of upsampling people in the trial who then might bear more risk of being in the trial, the groups that they're a part of would not necessarily have access to the benefits of the trial, at least in the presence of treatment effect heterogeneity.
I think that's an excellent question. So, you know, really just matching the distribution of the population you want perhaps isn't, you know, maybe you should make sure you get these people in them that you need to see. And I worried about this especially in machine learning because they don't even think about what's in the training and testing sets at all. You look at some LLM bias evaluation and they just said, well, I made up a bunch of stuff and we got, you know, 0.6. And, you know, they don't even tell you the information about what subgroups did they test, what were the analysis. So, like, we see things in bias trials where they say, oh, I just checked if Jewish people were greedy, you know, like nobody else. So, you know, I just made that up. But, you know, they only, like, they confirm their biases. So, I think this is a big issue. I think you should really learn to use good experimental design and think about these things when you do your machine learning.
Okay, thank you. So to follow up on the question that Andrea asked to Koske, whenever you will be building an algorithm, you will be using data that reflects and are also influenced by decisions that have already been taken. So you want to inform with these predictions decisions that themselves have already affected the data that you're using to do these predictions. And this, I think, was the question by Andrea. Do you want to, for example, include these variables, whether how the decision was taken or not? And maybe you want to condition or not on the variables that were used by the previous decision makers to actually produce data. So these, also, of course, raise all these issues on, because it could reinforce, you know, unfairness, but also bad or good decisions.
Right. So definitely, what I showed you is sort of, you know, it's very stylized, sort of assumed all the independence. But in this particular context, there's sort of two kinds of possible dependence at least. One is, you know, people who get arrested again, they come back, and they'll be assigned to the treatment and control. And so judge often remembers the previous decision, even though there are a lot of cases here. And there was one time like judge said, well, I overrode the algorithm last time and let you go, and now you got arrested, so this time you're not getting any pass. So there's like a sequential aspect, and judge sees the results and whether the judge was accurate or inaccurate for some cases, but not all cases. So there's that dependency. So we're trying to extend this framework to that type of situation. Another thing I'm currently working on is actually with the team at Stanford, where they have algorithm to assign refugees across different locations in the country. One in Switzerland, one in the US. And so they use algorithmic recommendation, and the human makes the final decision where they should go. And the outcome is things like employment and that they want to maximize. But there's a quota in each location. You can't assign everybody to one location. So there's like previous decision is going to start binding in terms of, So there's a lot of this kind of overtime dependency. But as far as I can tell, there aren't many people working in this area, at least among statisticians, like evaluation of these recommendations. So I really encourage you all to look into this.
Hi, everybody. Beth Ann from RAND. Thanks for your talks. I just wanted to bring up that I feel like this is yet another area where the mixed methods and engagement of stakeholders is going to be so key. The project that Liz and I are working on, a huge part of that when we build our personalized decision tool is supposed to be stakeholder engagement. I'm just wondering if you can talk about how, in your own experience, how has that been helpful? How has it been challenging? Because obviously there is a lot to learn from them to ensure fair work.
Yeah, I think that's, getting stakeholder involved is, in our case, many stakeholders are really busy, so it's hard to talk to them. So once they agree on the study, they're like, don't bother us. But, I think we did some interviews of judges. A lot of judges say, we don't look at those algorithms. But, humans can be influenced unconsciously too, so, yeah. But, when it comes to loss function and things like that, it's easy to write it down, but, what value to assign, that's critically important, and that's going to change the results. So, yeah, so those are definitely something that you have to work with stakeholders.
I guess I can say something. I mean, I got in this clinical trial equity space, and I've been amazed who found me, because it's not like I'm written tons of papers, and I work. Well, the National Health Service. I get invited to. We got best poster at the clinical trial symposiums and things like that. I think they're really struggling with how to do this. So they're looking for what are the proper ways so they could really use our house and we really should engage, It's a good startup or something. They're like, you should do a startup, it's a big problem for them because when we treated COVID and the vaccines, you got to deal with these issues of equity and fairness, and you want to exploit the data and you want to interpret. So I think they need that engagement and they're really seeking it.
Okay, I have a question for Silvia, which is about the definition of causal effect, which is based in your context on hard interventions, right? If I'm not wrong. So even interventions that are planned to be hard, meaning that they remove completely the dependence from the causal parents, may not be hard or perfect in practice. They may be more general, say. So I was wondering whether there exists alternative definitions of causal effects still based on graphs, but for more general types of interventions. Because, for example, there exists some literature on doing structured learning from data that are interventional but not hard interventional. But what about instead a more general definition of causal effect that one can then learn from observational data?
I guess, yeah, thanks for the question. I guess I'm not sure if I understand correctly, but at some point in the talk I said I will focus on hard intervention, but there are, like, indeed, as you said, very often, like, this cannot be implementable in practice, and so you need softer type of, or in other cases you might want to still take into account some context, and so perhaps not to just change how the causes affect, so the conditional distribution, the causal mechanism, but not remove the causes, or you might want even to change them. And so there is, I didn't go beyond in this work. I didn't go beyond hard intervention, but there is a concept of, like, this, what they call soft interventions, where you kind of change the general mechanism, the original one, with a new one, where you might change the parent. You basically change the conditional distribution with another one. We didn't work with this on the context of fairness in this work that that I presented, but in the one that I mentioned at the end on the designing fair optimal policies, there we consider, like, just indeed soft interventions, if you say. And also on the fairness work, we work a lot with soft intervention. I think it's nice. When the moment in which you start thinking about policies, then it makes much more sense to consider more sophisticated intervention than the hard one.
Okay, thank you.
So is there any other question? So let's say thanks all the speakers.
Yes, thank you, Anna. So, I wrote something because the other day I forgot to thank everybody, essentially. So, but again, before I say, come? Ah, davanti alla bocca. So, before again I say a couple of words of closing remarks of these two amazing days, at least for me. Carla and I would like to thank a couple of people who went unnoticed but were working behind the scene. And so these are two postdocs at the Dipartimento of Statistics in Florence, Veronica Ballerini and Giulio Grossi. I don't know if they are still here. Two assistants, Marta Mascalchi and Martina Zucca. Stefania, I don't know if she's here, but Stefania Petroni and her team at ENIC helped a lot organizing, and they've been efficient and nice also with you all, and so I would like to thank them also. So yesterday, when I said in Italian that the symposium was live streamed and recorded, to leave it to posterity, I meant it, right? So I said it in Italian because at that time, so yesterday, I didn't know how to say that in English, but I really meant it. And maybe this was too ambitious a goal, but the other day when Guido was presenting his journey as an econometrician to the Nobel Prize, he mentioned some quotes from Nobel Prize winners, including one by Andrea Ghez. She's the Nobel Prize winner in physics, I don't remember the year. And this quote says, "You should always explore things you are a little afraid of." And I must say, when we started embarking in the organization of this symposium, I was afraid. I was actually terrified. I was probably as terrified as I was terrified the first time I taught causal inference with Don Rubin. With Don Rubin sitting in class and me explaining his own work. So this was bizarre and terrific and terrifying. But these two experiences, so both the symposium and teaching in front of Don Rubin on his own stuff, had two effects on me, of course, causal effects. So the first is that I learned very fast. So it was a matter of, again, learning very fast and, be on top of things. And also they both made me think deeply. And so I think, again, the symposium has had this effect on me and hope on you all. So again, I hope this has been a fruitful and inspiring experience for all of you. A lot of you have traveled a long way to be here, so I hope you had not only food and beauty in return, but also some substance. There were some people like Francesca, Jali, who were asking whether, also Michela, who were asking whether this is only the first one and if we want to do another one. So at the moment, what I can say is that on Monday, I will take a couple of days of vacation. So we'll see. I think that I will try and bring some of the, let's say, flavor of these discussions, especially with the roundtables, within these causal inference conferences that we are organizing both in the US, the American Causal Inference Conference and the European Causal Inference Conference, that both have been very nice and but they are a little bit limited to statisticians and econometricians. I mean, they touch upon usually topics that are not as broad and as inspiring, I think, as the ones that were discussed here. Of course, we picked with Carla and all the people in the organizing and scientific committee these 4 topics and 4 keynotes. But of course, there are many more topics that can be covered. And so there is, in fact, scope for having tons of other symposium of this type, but of course it requires energy, so, I'm happy to contribute, let's say, but I will leave probably to Francesca to organize it in Boston or maybe Michela in Cambridge, but we'll see. So, safe travels back home and hope to see you soon, sometimes, somewhere.